Okay, so good morning, everyone from Paris, and good afternoon, everyone from India and the respective places whoever are joining this webinar. So I am going to present one interesting talk about some secrets about the Mesoproterozoic ocean story. That how the sulfide isotope can reveal and what new information we can gain from the mysterious period, that is the Proterozoic. So, to present this work, I take the pride to represent Geological Survey of India, who is celebrating his 175th years of anniversary this year. And fortunately, in the 9th December, I also completed 12 years in this organization. So it's a great pleasure for me to represent my organization in front of you. So, as you can see in this first photograph, this is the CAMECA SIMS IMS 1300 HRQ. The most advanced large geometry SIMS made by CAMECA is installed in the Geological Survey of India, and it is located in the Kolkata. So it has been installed in the month of September 2022. Till then, we are trying to do stable isotope analysis of different elements to make some meaningful information about the geological information of our ancient past. And you can see a beautiful picture of the different sulfur isotope masses that are isobarically resolved by optimization of the chemical SIMS instruments. And so with this, I want to go ahead with the first, with the beginning, why the sulfur isotope is important, or why sulfur cycle of the earth is important to know. Just whoever is not acquainted with this topic, for them the sulfur is the most abundant sulfate is the most abundant anion in the marine water after chlorine, and the sulfur is one of the key element that links with the atmosphere, hydrosphere, lithosphere, and biosphere, and the interaction goes on past beyond the ancient Archean to the present time. So the it is a master one of the master element that plays a different role in shaping our planet at different geological times. So this alpha cycle, if you try to understand how this work with the interaction between the atmosphere and biosphere and the hydrosphere, so the simplicity diagram I took from the Wikipedia, it described nicely that the surface oxidation of the pyrite by the river water or the rainwater carries the sulfate to the marine ocean water, and the surface of the present day marine ocean water is highly oxidative. So sulfur remain in sulfate condition in form of dissolved sulfate, and by reducing in the bottom of the ocean, when the sulfur reducing bacteria reduces the sulfur to the sulfides, and with the presence of dissolved iron, it gets precipitated by the in form of pyrite. So the fixation of the sulfate to sulfide in the ocean bottom water is going on in the present day, and again the pyrite that was precipitated at the ocean bottom get oxidized again to convert it into the sulfate. So this sulfate and sulfide cycle is going on in the present day ocean. So now how these information are useful to decode our ancient past, or what happened in the ancient past about the in shaping our understanding about the atmosphere and biosphere interaction. So usually these records are kept beautifully in the sulfur isotopes signature, and I must say the most useful is the del 34s, that is the ratio between the 34 by 32 sulfur isotope. So it gives immense information about the microbial metabolism, because the sulfur was one of the electron donor that was taken up by for metabolism by the anaerobic bacteria. Then it tells about the oxidation state of the ocean chemistry. That means how either it was oxidized ocean or reduced ocean. So that information you can get from the sulfur isotope, and how the atmospheric evolution. That means the oxygen level increase or decrease in the Earth atmosphere was directly replicated by the oxidation states of the sulfur, and so with this huge, immense importance of the sulfur in understanding the ancient processes, we go ahead with the sulfur cycle, import significance of the sulfur isotope, what I was talking about. This is a beautiful diagram published by Fakri et al. Recently, which explain nicely the different forms of sulfur, its transportation in different medium in lithosphere, biosphere, and atmosphere. The sulfur here in the left image is getting released from the mantle of the deep crust by the volcanic product or the volcanic degassing, and then it transferred to the atmosphere, get reduced to the hydrogen sulfide, then get precipitated as iron sulfide in the ocean bottom condition, and again it oxidized, and this process goes on. Similarly, since it is the sulfur is having, I told that it has different redox potential capacity. So sulfur isotope is sulfur is very sensitive to capture the global oxidation event. That nicely can be answered at different geological times, since the sulfur allow to measure the oxygen fugacity very precisely and quantitatively, and the availability of the electron. And next is the microbial activity, which is mostly the dominant of today's talk, that I will explain step by step. And the next one is how the ocean and atmosphere coupling and decoupling took place in the ancient part, and the evolution of a complex life, because sulfur is one of the element that is the one of a major component in the amino acid and the protein. And most importantly, whoever are the exploration geologists, the ore forming environment is broadly controlled, or it has been taken up by bisulfide ligand, or for transportation of the metal from a source region to the sink region. So, so these are the things that sulfur can tell us, and that's why people are more fascinated about studying the sulfur over geological times. So, what are the major sulfur sources that I already discussed is the riverine influx of the sulfate by the continental weathering and erosion, and then sulfur get precipitated by reduction of the sulfate to sulfide by microbial sulfate reduction broadly. Then another important factor is the sulfur disproportionate and the hydrothermal sulfur reduction. And again, the fixation of sulfate to sulfide by conversion from barite to pyrite, or the calcium sulfate to the hydrogen sulfide. So if we understand, try to understand how the interaction between the crust and mantle is going on in terms of sulfur, then the mineral like the iron sulfides and other sulfide mineral fixed or the precipitate at the ocean bottom, getting subducted below the continental crust, and the sulfur is going down to the upper part of the mantle. Then again, the upper part of the mantle is getting metasomatized and remelted and getting back in form of the volcanic arc. So these processes are going on, and what we call or broadly understand as the sulfur cycling. But here, what I wanted to mean about the sulfur cycling is the biocycling of the sulfur, which is another fascinating factor, because it helps us to understand how the biological or the life came into the earth, how it evolved, how the metabolism was going on, and all these processes. To the right side of this diagram, sulfur takes 32, the other lighter isotopes among the other, as his metabolism during his metabolism, because the 32 sulfur compared to the heavier mass 34, it has a reduced mass and higher vibrational frequencies and lower activation energy. So it easily breaks the bond and take the 32 lighter isotopes for the metabolism. And it has to be, the process is controlled by the kinetic fractionation process, because here the organic matter, that is the main electron capturing agent over the here, it reduces the sulfate in the ocean bottom, the dissolved sulfate, and converted it into the hydrogen sulfide. So here the hydrogen sulfide is a metabolic waste product, and the sulfate is the terminal electron acceptor. So what we call this reaction I mentioned over here is the energy harvesting respiration process. By anaerobic bacteria. So if we try to understand in a simplistic way, the cartoon diagram says how sulfate is fixed as sulfides by the microbial or organic matter. So moving forward, why the Proterozoic? Because this period is always fascinating to me because so many things was going on around this period. So Earth was going through major changes from during the Proterozoic, and very minimum information is available very confidently within this time period. And these two diagrams by this Fakre et al. Defines very nicely what was going on actually. The sulfate condition after the great oxidation event around 2.4 billion years drastically changed this period because the oxygenation of the sulfides dissolved in the marine water and in the continental crust. So the sulfate levels certainly get enriched and then again reduced, but is steady state because at that period the oxygen level of the earth was increasing slowly but very sluggishly at a steady, almost steady state rate. And if you want to see the fractionation of the pyrite, the sulfur residue fractionation between the pyrite and the sulfate certainly increases in these periods, and the atmospheric oxygen level increases certainly after the great oxidation event, but it was steady state enough. So similarly, using these parameters, people tried to understand how Earth changed in that time, and also additionally, plate tectonism was getting was going through a major changes from a subduction dominated plate tectonics to a continent collision or rift related plate tectonics during that period. So what popularly known as from accordion style plate tectonics suddenly introduced by that time. And this time the ocean was usually stratified and eugenic, but how much eugenic, how much oxidized, these information are not readily available with a very solid proof. So getting that proof about the ocean chemistry and eukaryotes were suddenly emerging in that period. So biologically, tectonically, this period is very interesting to understand about the evolution of our earth. So with this idea or with this concept about the sulfur cycling and the Proterozoic period, I now want to introduce you one of the interesting basins from the central part of the India, that is in the Bastar Craton. So Bastar Craton is located basically center of the India, and it is a Archean cratonic nuclei with many intracratonic rift basin developed over during the Proterozoic time. So one of that basin is the Chilpi Basin that is located in the northwestern margin of the Bastar Craton, and the Chilpi Basin is very similar to a very shallow marine intracratonic basin. So when we map that basin over the different parts around this basin, we found a very simplistic, undeformed, unmetamorphosed lithological sequence down starting from the basal conglomerate with the polymictic crust dominated to the matrix dominated conglomerate, followed by a followed by a purple color quartzite, and it is a cross-bedded quartzite, followed by a ironstone, which is very unusual in look. I will discuss. Then it followed upward by a carbonate sequence that is basically a limestone and a felsic tooth. So this is the broad lithology of this area, and so our primary assumption was this depositional environment was a very shallow continental shelf to marginal marine basin, followed by, and there are, you can see these are the basement granite exposed in between the basins. So these are the basically basement high. And from that perspective, it was clear to us that this basin was not a very deep marine basin, rather a shallow marine basin. Because why I am saying this, it has some importance with what I am going to talk next. So what was the age of the basin was interesting, but it was not dated directly. But I can show you the conglomerate at the right bottom corner. It contains the class of dolerite dikes, which have been dated elsewhere in the Bastar Craton, and the age of this dolerite dike is between 2.1 to 1.88 billion years. So we bracketed the age between 2 and 1.6 billion years, because in further east, this basin is overlain by a further undeformed sedimentary sequence of 1.6 billion years, which has been dated precisely by the from the felsic to zircons from the felsic 2. So we bracketed this age of the deposition between somewhere in 2 and 1.6 billion years. So the most interesting part of this Chilpi basin is the carbonate and the ironstone unit. You can see the unusual unusual texture in this ironstone, which is not a characteristics of depositional or neither a characteristics of a hydrothermal vent system. So our initial assumption was kind of biogenic activity is preserved here, or something is going, something is wrong. It's not usual in the sedimentary deposition. Then moving forward, we found a very beautiful domal stromatolite structure in the limestone unit. And these stromatolites are not big enough, but their synoptic relief is not high enough, but these are preserved in different layers of the within the limestone units. And we were very lucky to get some diagenetic pyrites from these limestone units within this stromatolitic horizon. So we thought, why not take these pyrites for sulfur isotopy analysis to get some idea about the ancient microbial effects. So I can say this Chilpi is one of the natural archive here that is preserving the carbonates with these pyrites, which are very rare in the Proterozoic. And also these proterozoics are these sulfides, if we are able to analyze with a high spatial resolution, it can resolve the multiple generation of growth, if any existed, and we can get an idea about the post alteration or hydrothermal or metamorphic impact that we can exclude from the other diagenetic processes, and if any overprinting is there, that we can cautiously avoid. So what when we cut those samples perpendicular to the stromatolitic layers, we found something interesting, that the stromatolitic layers are within this microbialitic layer. There are pyrite and celsian that are syn sedimentary and preserved within the stromatolitic layers, and pyrites that is absolutely post depositional and not spatially linked to the barite and uh, that celsian. So barite and celsian first hand give the idea that the oceanic condition was oxidized enough to make sulfur to the sulfate state, while the pyrite gives an idea that the environment certainly changed from sulfate to sulfides, and this is the ideal condition what we are looking for any microbial activity is present or not. And if in the EDAX ion imaging shows these pyrites are absolutely chemically homogeneous. There is no, even the backscatter imaging shows, the quadrupole data shows there is no chemical heterogeneity across the pyrite grains. And if you see these photographs, there are radial diagenetic growth of potash feldspar, quartz, and calcite around these pyrites. So it was another proof that the pyrite growth was post-depositional, and these diagenetic halos were the pathways where the elements were migrated uh, to build the pyrite at the late stage. And again, one interesting fact is that many of the pyrite grains were marginally again re-oxidized to magnetite. So we are getting a sequence from a barite to pyrite to magnetite that represents a completely oxidized, reduced to re-oxidized situation. But we are not sure from these photographs or the images, the oxidation of the pyrite when it happened. It could be a phenomena of the present time, or it could be a phenomena of ancient past, but that we cannot say. But from these images, it was very much confirmed that pyrite was grew diagenetically, and it is post dated to the barite. Even it is post dated to the entire micritic limestone deposition. So here the SIMS is the master player who helped us systematically to solve many questions that I will discuss. Because uh, if we were not allowing our samples to be analyzed for the sulfur isotope by very high spatial resolution, we could have mixed many things. So here I want to say a few words about the precision and the uh, data quality we gain from the using the CAMECA IMS 1300 SIMS. So the analytical condition here, we use the 133 cesium plus primary Gaussian beam. We used an energy slit of 30-fold electron volt with a beam diameter of very small size of 5 to 8 micron, and contrast aperture fully open. With the following condition, we found a very precise 34 by 32 ratio of the standard pyrite grain, and the precision is better than zero point 0.2 per mil for the entire datasets of 50. So that much of precision is required to resolve here the many questions. So when we targeted with this much of precision with the our samples, and we took many profiles across the pyrite grains to see the any isotopic heterogeneity is there or not, while these are chemically absolutely homogeneous. So we found very interesting thing that the large grains, which are more than 100 micron in the size, are made up of a lighter del 34s core and heavier del 34s rim, and it is mostly recorded along the large grains, while the small grains, they are having flat del 34s profile. So there are two distinct clusters of the del 34s across the pyrite grains. The core are made up of basically lighter isotope, while the rims are basically made up of the heavier isotope. So our interpretation was that the microbial sulfate reduction took place here over the other processes in the during the diagenesis or during the generation of the pyrite. So to rule out, we first wanted to rule out the thermochemical sulfate reduction, which is naturally operational above the 150 degree centigrade temperature in the petroleum or the oil window, what we can say. So what we took is a conventional method to calculate the burial temperature. We calculated the approximate surface temperature. We taken the approximate surface temperature of the Proterozoic time, that is 20 degrees centigrade, from the published literature. We calculated a burial depth in kilometer from the conventional method that two-thirds of our present day chill horizon is eroded out, and from the basement high and the basement exposure of the window present here, the basin was uh, not deep enough, and the geothermal gradient of the Proterozoic time, that is 35 degrees centigrade per kilometer. So we found that the maximum depositional temperature of the burial temperature was 40 to 45 degrees centigrade. So the 40 to 45 degrees centigrades are not enough to for the thermochemical sulfate reduction. So the preliminary idea was that the kinetic fractionation took place in generation of this pyrite. So we modeled this with this concept. We that sulfide equal to del 34 sulfate into epsilon, which is the net kinetic isotopic effect, that is alpha minus 1, and the remaining fractionation of the sulfate in the pore water of the system from where the sulfides are getting crystallized. So the value was, we found, and we did this calculation for a large epsilon range that are well valid for the Proterozoic, that is from minus 30 per mil to minus 40, 50 per mil. And we found a good match with the epsilon value with minus 35 per mil. So our data says there are 8 per mil maximum difference from the core to rim uh, of a large pyrite grain. So the data says that the initially, while core was forming, the sulfate 74% sulfate in the system was already reduced by the microbial activity, while the rim was growing at the outer part, the fractionation factor was 0.59. So around 28% of the total sulfate was reduced by the sulfur reducing bacteria while it was growing in a semi-closed system. Why we are saying the term semi-closed system over here? Because if barite had a direct control for dissolution of barite to grow up the next sulfides, so barite could have reduced the sulfur isotope value at the margin also. But what we see here, the barite is present here texturally or spatially at different place to the pyrite. So the initial or the final assumption was that pyrite was going isolate condition than the barite from basically the pore water sulfate, and the barite dissolution was restricted to very locally or very local pore space condition. So we developed a model like that the Chilpi sediment says that it was a stratified ocean condition. At the top part of the ocean, it was oxidized, where the barium and barium was possibly supplied from a volcanic input, and the barite was precipitating with the microbialites or the stromatolites as thin sedimentary product at the top part of the or I must say it's a ocean water interface. Water and the sediment interface, the variety was going on. Then, while during the deep burial, during the diagenesis, the sulfate was getting reduced to sulfides locally from the pore water, and the pyrite was getting precipitated. So the cartoon diagram, we tried to explain this systematically, how this pore water diagenesis and the sulfide growth was going on, and how microbes were playing the role. And there was no report of the stromatolite and microbe previously from this area. So this paper we have published in 2025, which explains all these processes. So I want to say about the bigger processes, how this study advances our understanding about the Proterozoic. It's a rare record where we are getting both the mineral archive. One is a barite that is already a oxidized or relatively oxidized product, and it's getting precipitated directly from the seawater sulfate composition. So barite composition is typically depicting what was the sulfur isotope signature of the seawater by that time. Then the pyrite composition is directly a proof that the microbial sulfur reduction process was going on in the pore water beneath this barite when it was in a deep burial. So this is a clean separation and is a rarely preserved in any Proterozoic sedimentary basin. So this mineralogical partitioning of sulfate and sulfide from these Proterozoic records says that the Proterozoic basin was uh, already classified in different layers. And there is a direct microscale evidence that there was a low sulfate ocean. If the ocean sulfate was available, then this 8 per mil deviation between the core and rim was not possible. And also the sulfate, the lighter core and the heavier rim says that the microbes were taking the sulfate as their metabolism activity, and it was reducing to from sulfate to sulfide. So it is one of the cleanest Proterozoic examples that the sulfate trap MSR preserve inside a single pyrite grain. And also we have used many proxies to calculate what was the sulfate concentration of the Proterozoic basins. But in this case, this pyrite or the single grain of pyrite or multiple grains of pyrites directly saying that the Proterozoic basins or the ocean was very poor in sulfate concentration. And the third point is that uh, the vertical structure of the mat ecosystem, what I told, and I tried to draw a cartoon diagram over here. The stromatolite and the barite, This together says that oxygenic phototropes was present over there while the stromatolitic lamination was going on. And in the middle part, the iron, as we all know, the Proterozoic oceans were full of iron, but it was not oxidizing, or the Fe was in Fe2 plus condition and stratified ocean condition. So microbes for their fermentation or their for nucleation activity, they require reduction of the Fe2 plus, Fe3 plus to Fe2 plus. So this is the ideal place to see how the systematic reduction of the different element was going on from first initially the iron reduction followed by the microbial sulfate reduction. So in one or two photographs, there is a direct petrographic and isotopic evidence that the Proterozoic mat were stratified, and it is a not inferred, it is direct evident. And the next, the Fe reduction was important early because the competition between the metabolic competition between the SRB or the sulfate reducing bacteria, the metabolic sequence is followed by O2 greater than NO3 greater than manganese greater than iron, then sulfate and CO2. As we know, the oxygen and NO3 was already low in the Proterozoic ocean and Proterozoic atmosphere. So the dominant competition was between the iron and sulfate. So first, the microbes need to reduce the iron. Then when the environment chemically changed from Fe3 plus to EH4 domain, then microbial sulfate reduction took place in the domain. And the methanogenesis was suppressed by that time because methanogenesis and sulfate reduction cannot go hand by hand. So methanogenesis was stopped by that time. And the pyrite del 34S zoning completely captured these processes, and this exhaust then we wanted to know how this iron stone and the limestone or the stromatolitic limestone are correlated in this Proterozoic basin. So the answer lies there. The cyanobacteria first created the anoxia locally by reducing the Fe3 to Fe2 plus. Then the Fe2 plus was readily available for for precipitation of the pyrite, while the Fe2 plus again reoxidized with the interaction of the ocean bottom water to get precipitated the iron stone. And this microbial activity was directly linked to the iron precipitation over here. So this says the MSR, the boundary between the MSR and Fe reduction, the timing between the methanogenesis, how you can quantify these processes in the ancient past. And again, we wanted to know or we wanted to conceptualize when the organic matter exhausted. And so this answer also lies over here. Once trapped, the organic matter is largely consumed and the sulfate concentration is pretty low. By that time, microbial sulfate reduction, uh, it was near to close and the pyrite stopped growing, and the final isotopic band in the crystal mark possibly the last breath of the microbial activity in that microenvironment. So that kind of immense information from 2-3 single pyrite grain we can gain, and these are the important and vital information because these are not readily available from the Proterozoic basin, which is already an enigmatic period. So to finish off this, so how these ironstone, MSR zone, pyrite, and limited sulfate concentration enriched us. So it says that the Proterozoic water column remained ferruginous. So it was a long-standing debate between the different workers who are deeply involved in the activity of to know what was the Proterozoic ocean condition. So the pore water beneath the stromatolite was microsulfuric. So there was not that the ocean bottom was entirely sulfide rich. Rather, there were pockets or the pores which were already reduced, and the sulfur emitter was going on. in these zones. And this helps us to contribute on the long-standing debate that not fully oceanic oceans in the Proterozoic and also not fully ferruginous. So it's a mosaics of iron-rich water and sulfide-rich microenvironments. So we believe that it adds an important information to the science of Proterozoic in understanding how the Earth was there and how the Earth was evolving and transitioning between that period from Archean to the modern Neoproterozoic sequence, which is more similar to the modern oceanic condition. So, uh, so to sum up all these things, this study provides an uniquely integrated record of seawater sulfate condition that is very low. So MSR dynamics, how the dynamics of the microbial sulfate reduction was controlled very locally, and what was the microbial mat structure that is very much stratified, and how this iron cycling was going on in the ocean, and what was the diagenetic evolution in different basins. So these all preserved together in this stromatolitic limestone from the central India. So these are the few references I want to add. I have used these diagrams, and thank you. So this is the GSI SIMS group working presently in the SIMS laboratory, and we also invite collaboration across the world to solve many more histories about the Proterozoic and other time periods to make our understanding better about our Earth. Thank you.